Hey, so doing a special IOH. It's a workshop and it's happening at GraphHack. So it's the first somewhat in-person indexer office hours, and we're going to touch on some developments, new developments that we're working on for the indexer stack. So I'm going to start. I'm 𝗨𝗂𝗂𝗂𝗂𝗂𝗂 from 𝗨𝘀𝗲𝗂𝗂𝗂𝗂𝗂 Labs, and I'm going to talk about AutoAgora, which is a cost model automation tool for indexers that we've been working on for the past few months. That's largely derived from our study of query complexity and query costs, for also in parallel building a neural network that is for predicting the complexity of queries. So this is a lower hanging fruit that's spun off from that effort. So yeah, let's get in there. So AutoAgora has two main purposes. It helps build automated relative costs between query shapes, and also absolute costs that adapt to market conditions. So I'm going to start with how we do relative costs discovery. So as you may know, this is a small Agora model, and pretty much an Agora model is a list of query shapes for which you define a price. And so this is a pretty hard job because you have to regularly run statistics on the queries you've seen and decide manually which query shapes you want to create a specific price for. So it's a bit of a tedious job that you have to redo regularly and for each subgraph, etc. And so as a matter of fact, we know that most indexers will just do this. Just a flat price because it's easier, it gets you going, and yeah, it's easier. So we're trying to improve this. So first, I'm gonna give a little bit of a of context on query complexity. So we have measured. So here in particular, it's Uniswap v2 queries. We have measured that many queries can take upwards of 10 seconds to execute, while others take 10 milliseconds, right? There is a huge spread, and those long-running queries are particularly rare, right? So we do need to take them into account, and because they impact our server's performance so much, we really need to price that in, right? And also disincentivize bad queries, right? Disincentivize app developers to send us very bad queries. So here in particular, we can see that we can easily span 3 orders of magnitude in terms of execution time. So it's very large. What we also see as indexers is that usually we don't see that many query shapes. There is of query shapes that represent 99% of the queries we receive. So it shows that it's possible to catch most of the queries we're seeing within a reasonably sized Agora model, because we're also trying to not break the gateway and the indexer selection algorithm. So we want to build somewhat reasonably sized Agora models that serve us well, right? So for this, so this is the stack for the AutoAgora relative cost discovery. So I'm gonna go through the various components. So the indexer service, all the queries from the gateway are going through the indexer service. We slightly modify the indexer service such that it sends detailed query logs to what we call the AutoAgora sidecar. Sidecar's job is only to send that to a RabbitMQ queue that helps us relieve back pressure on the standard output of the indexer service. These unprocessed query lines go through the AutoAgora processor. The processor does is that it unpacks the log lines, normalizes the queries, separates the queries into what we call a query skeleton, or we call it also a query shape, and the variables. And we store all of these logs into a Postgres DB. And then we have the main AutoAgora component that will use the data from the Postgres DB to determine which query shapes should be used for building the Agora model for particular subgraphs, and what price should be set on those, right? We also have a little bonus component from that AutoAgora. That's the revenue metrics. We measure the query fees that are paid for each for every single query, and we accumulate revenue metrics that we serve to Prometheus, such that we can have a real-time graph of how much we're paid for the queries. So yeah, that's the overall idea here. So here, just wanted to show you what those new log lines look like from the indexer service. And so we got the time, so that's useful for a timestamp for the logs. And we got also the deployment, the fees that are paid in GRT, and the entire query string that contains the actual query, as well as the variables. We measure from the indexer service also the execution time of the query. So that's all the information we're using for AutoAgora. So I'm going to go now more in detail into those different subcomponents. So the AutoAgora processor will ingest the log lines from the RabbitMQ, and will extract all the data from the JSON-L and normalize the query. To normalize the query, it will also use the subgraph schema. I'm going to show in the next slide why. And so the queries are separated into query skeleton or query shape, for which we compute a hash, a cryptographically secure hash in this case, so that we're sure that consumers cannot attack our cost model and escape it. So the skeletons are saved into one table, and the log lines that contain the timestamp, the variables, the subgraph are saved into another table. So that's a form of compression. So I'm going to show you also later how that compression helps here. Query normalization is quite complex, as you can see, many boxes. But the gist of it is that so we ingest the query plus the variables, and then we substitute fragments. We then factorize. So that's when you have multiple selections with the same name, you put them together. We prune the arguments. Turns out that in GraphQL queries, you can repeat the same argument multiple times. Only the first one counts, so we prune the extra ones. Then we do a lexicographic sort of the various nodes in the GraphQL query. Remove the unknown arguments, because that's also something that's for now authorized on the graph node. And then we split the root queries, remove the values and put them separately as variables. Build the variable definitions. That's also somehow not mandatory on the graph node, but per the GraphQL spec, it is. So we're building those. We're removing the query name, and then we strip the whole GraphQL string of all extra spaces and new lines. And that's our query skeleton. So first here, just to justify why we're doing all those things. So here we have two histograms laid on each other, and we're showing here the 10 most query skeletons. And we can see that, so in blue, it's before normalization. You can see that the buckets are getting smaller pretty quickly. And after normalization, we get much larger buckets. We can bucket way more queries together that look different, but are actually the same, right? That's pretty important, because when they get executed, it's the same thing. So it does work. It makes a huge difference. So what do we get out of those, all those steps, all the processing? So we get a logs table. So you can see here, subgraph query hash that we use to find what the corresponding query skeleton is, timestamp, execution time, and the variables that are used for that particular query that we received. And then we can reconstruct what the actual query is by reinjecting the variables into the corresponding skeleton from the skeletons table. That's pretty much the idea. That's how we compress things. And we've done some measurements. So here we run it for about 500,000 queries, and it was, I think here it was a handful of subgraphs, about 5-ish subgraphs that we were running, and we got only 64 query skeletons in our database. It's pretty good compression here. So it's quite useful. Yeah. So then, how do we build the actual Agora model? For now, we have a pretty simplistic way of doing this. We just look at the most frequent query skeletons for each subgraph. We compute the average execution time that we've observed, and just format an Agora source document and push it to the indexer agent. And then what you'll see in the indexer CLI is those kinds of entries. So here it's for one subgraph. Turns out that we got two query skeletons that were that we saw, enough times such that they were eligible to be included in our Agora model. And just for convenience of the indexer, we're adding as comments some basic statistics: how many times we saw the query, what's the minimum time, maximum time, the average and standard deviation. And here we set a price. And what you can see here is that there is that global cost multiplier. Here, it's pretty much, this is this component here is pretty much the average execution time in milliseconds. But then we have to adjust this, shift all of those values to have some reasonable GRT price for those queries. So that's what that global cost multiplier is. The problem, though, is what should be the value for this? And there isn't really an obvious answer. It depends on the subgraph. It depends on how many queries are executed against that subgraph on the distributed network, how many indexers are serving, and what the other indexer's cost model is. So there's lots of variables going on here. It's a dynamic market, so there's no good value, no safe value here. So that's why we also have a subcomponent that does absolute price discovery in real time. So you may have observed when you're playing with even with a flat cost model, that as you shift your pricing, the queries that you receive, the queries per second you receive will change. So if you set a very low price, you will get quite a lot of queries. There's somewhat of a plateau, right? And as you increase your price, the number of queries per second you receive will sharply go down, all the way down to the 0 queries per second plateau, right? So you can guess that you want to be somewhere over here. That's where you'll make the most money. That's the market price, right? Another way to show this is to compute a revenue per second metric, which is pretty much the price times the number of queries per second. And it looks like this, as you may have expected. And you want to be here, right? Maximum money, of course. So for this, we decided to employ some continuous reinforcement learning to find that optimal point. And the model we're using right now is a Gaussian probability distribution function that is over the price multiplier, and we learn the we learned the mean and the standard deviation of that Gaussian, such that it converges to the market price, the optimal market price. So the idea is you sample that Gaussian for a price multiplier, you apply it to your Agora model, you wait 2 minutes. So that's the time we have to wait for the gateways to take into account our change. You measure the number of queries per second you get, and then you update your policy, your Gaussian policy, using the revenue per second as the reward. And that's probably pretty much what most indexers would do when they want to manually tune their pricing. You try a value, you look at how many queries per second you get, you try another value, and you try to kind of like narrow down progressively where the market price is. Problem is that it takes hours, and it also changes over time. So technically, you would just poke around, you would just sit in front of a computer and do it all day long, right? Not very realistic. So yeah, so this is what we get in simulation. The red curve is the number of queries per second. We added a little bit of noise to make it a little bit more realistic. And the line in blue is the Gaussian probability density over the price multipliers. So we can see that when we start, it's extremely wide because it doesn't really make very strong assumptions as to what the optimal price multiplier should be. But we can see that it pretty quickly converges towards the optimal pricing. And as the market changes, the Gaussian tries to follow the optimal point. And we can see that it never really sharpens very strongly. The standard deviation remains, I mean, it doesn't go to 0, right? And that's where we want to balance exploration and exploitation. So that's a pretty tricky problem to solve. And you have to continuously sample a variety of values such that you know where you are. You cannot just select a price and stop there, because then you never know if the market has changed, right? You have to see what the slope is on your revenue per second curve. The only way is to try different values all the time. It's just that you want to try values that are that stay pretty close to the optimal point, right? That's pretty much the idea. So here there's less data flow involved for this. What we're doing is that we are tapping into the query metrics from the Prometheus probes that the indexer service is serving, and yeah, just use this to measure the number of queries per second, and execute the reinforcement learning algorithm. And this is what we get. This is a pretty good run, and we can see that it took that's about 13 hours long on that scale. We can see that. So this is the mean, and this is the standard deviation. So we can see that the mean is slowly shifting over time. It's slowly going up, and the standard deviation is going down because that's the agent being quite confident about its pick. And we can see also, so that's linked to the standard deviation, that the sampled values are narrowing down over time. And we can see also probably the metric you're most interested in, the GRT per second we're making is going up over time. So yeah, that's a good result. So if we put all of this together, these are all the components. So just to make it more obvious what's our contribution here. The blue boxes are ours. We're also and you'll also have to add a RabbitMQ instance and maybe a new Postgres instance, or use the one you already have. And yeah, that's pretty much the idea. That's the whole thing. So there are some limitations to this for now. It's still in development. So for the relative costing, the modeling we're using for the relative costing of queries is pretty simplistic, because it's only based on the observed execution time from our logs. Also, for now, we don't have an execution time for multi-root queries. So the technique we'll have to implement is to rerun ourselves the subqueries that we've extracted from multi-root queries, such that we can get an execution time. For the absolute costing, it's pretty slow because of that 2-minute wait that we have with the gateway. It's somewhat unstable on low queries per second subgraphs. We're working on a mitigation for this to not have the reinforcement learning running on low queries per second subgraphs, because there isn't much to learn anyway, and there's probably not much money to be made anyway. So you might as well set a reasonable price such that you can still deliver a good quality of service. Yeah. And one last thing that's more theoretical, it's a little bit more involved, is that we don't have a proven stability of that system when you have multiple competing reinforcement learning agents on the same market, on the same subgraph. You could imagine that there could be some oscillations as the different agents are trying different prices. Because as you try different prices, you're also influencing the market price. So yeah, we don't know what can happen here for now, and we are working on a. So the big warning: this is alpha software, so don't just jump in there and throw it on your indexer. Number one priority is quality of service, so we have to be careful. So yeah, be very, very careful with this. For now, maybe the best thing to do is to discuss and study it, and for you to study the code, and you could also contribute. That'd be awesome. But yeah, please be very, very careful. So here are the repos. So there's the AutoAgora processor, AutoAgora sidecar, already explained what that is. And then we also have a repo for that we call the GraphQL utilities. And this is for normalizing and fixing GraphQL queries. So that's what we use for normalizing things here. That's also what we use for our machine learning efforts. So yeah, that's it.